Okay, inverse functions. So let's learn about some inverse functions. So you can get an inverse of a function by looking at all the ordered pairs of that function and have them reversed. So for example, if the point a comma b is found in your function f of x, then what we call the inverse would be switching the 2 points, becoming b comma a, and that's going to be on your inverse function. Okay, and we denote the inverse function by this notation with an f and this -1 on the superscript of x. And it's read as f inverse. Okay, and it's very important to note that when we talk about inverses, that -1, that's not an exponent. It's just a label. It's just a way for us to present the inverse function as a specific notation. Okay. Now, in some people might think, well, is the inverse function just 1 over f of x? Is that kind of a reciprocal? No, it's not. Okay, it's very, very specific. We're looking at what happens when we reverse x and y. Okay, and it becomes y and x. That's what helps us define our inverse function. Now, the inverse function may or may not be a function. It just may be a relation, but it may not pass the vertical line test. So sometimes the inverses are not functions. Okay, so how do we determine the inverse function for any given function? It's pretty simple. If you have a table of values or a set of ordered pairs, you just reverse your x and y. So you go from x and y to y and x. If you have an equation, we're going to be solving the equation by, or determining the inverse function by switching x and y, and then solving for y. And we're going to then use the resulting equation and write that in inverse function notation. And for if you discovered in the Desmos activity, the graphs of all inverse functions are reflections of the original function on the line y equals x. So think of y equals x as your mirror line. All functions are reflected on that. Okay, so let's look at some examples. Determine the inverse of the function. So here we have a list of ordered pairs. So to determine the inverse of the function, we're going to reverse the x and y pairs into y and x. So my inverse function, f superscript is -1. So f inverse of x equals curly brace brackets because my set notation. And now reverse the coordinates. So 0, 3 becomes 3 and 0. Next we have 3 and 1. Then we have 3 and 2. 3 and 3 just stays as 3 and 3. And then we have 4 and 3, which becomes 3 and 4. And then 5 and 3, which becomes 3 and 5. And there you go. There's my inverse function. Is the inverse actually a function? So let's check. Well, if you notice, my x values are now all 3, and my inputs have more than one output, right? 0, 1, 2, 3, 4, 5. So it's not a function. So we're going to say here, no. The input of 3 has multiple outputs. All right, let's state the domain and range of our original function. So look at the original function. The domain is, well, 0, 1, 2, 3, 4, and 5. And the range of f of x is just 5. Or just 3 rather. All the y values are 3. But if you look at the inverse, it's a little bit different. It's just the domain is now the range of the function. So domain is 3. And the range for my inverse is the domain of the original function, 0, 1, 2, 3, 4, 5. Okay, so what do you notice? Well, the domain of f of x becomes the range for the inverse. And the range of f of x becomes the domain for the inverse. So they switch, and that will always be true for when you're talking about finding the inverse, comparing the inverse function with the f of x. Okay, so let's look at a graph. So let's sketch the inverse of the given functions. So you're given a graph, how do you sketch the inverse? Well, it might be useful to look at some of the points here where things are happening on this graph and writing down what those coordinates are. So if we assume every square is one unit for my scale, we can determine the coordinates of the points on this graph. So I'm going to have -5 and +2, and here I have -3 and 0, and over here I have 0 and +3, and down here I have 3 and -3, and then 5 and -2. Okay, so my inverse function points would be just taking every single one of these coordinates. I'll go from left to right and then switching their x and y. So here I'm going to have 2 and -5, 0 and -3, 3 and 0, and -3, +3, and then -2 and 5. Okay, I'm going to plot those points on my grid, and we'll get the inverse afterwards. So 2 and -5, 0 and -3, 3 and 0, -3, and +3, -2, and +5. Okay. Now it's just a matter of drawing the connections properly to make it look like it's been reflected. So 2 and -5. So if you want to, it helps sometimes draw the function y equals x. Let's draw y equals x first. All right, let's use a different color. So there's my y equals x. So all functions are a reflection along this line. Okay. Okay. So let's see, 0 and -3, right? Okay, so then we can now we can reflect. Okay, now we can reflect. So I'm going to have a connection here. Then we have, let's see, this gets reflected over here. And then we have another one over here. And then another one over here. Oh, that doesn't look quite right. One, two, three. Oh, this last point should be down here. There we go. Okay. And there's my reflection. So maybe you have to tilt the graph a little bit to see it clearly. Okay, but what I'm looking at here is if I look at this portion, that's reflected along this side over here. If I look at this portion, that's reflected over here. And if I look at the lines that cross these two, those are reflected. And then these two are reflections of each other along the line y equals x. So you might want to turn this thing vertically to see the much more clearer reflections. But that's how you do it. Okay, so we looked at ordered pairs. We looked at the graph. What about an equation? So for an equation, what you have to do is, just rewrite the equation as y equals 3x plus 2. Okay. And what you can do is reverse the variables. So now I'm going to write this as x equals 3y plus 2. So in other words, you're switching places. So x and y becomes y and x. And now you just have to solve for y, isolate for y, okay? So if I subtract 2 from both sides, I'll have x minus 2 equals 3y. And then if I divide both sides by 3, I'll get, right up here, y equals x minus 2 over 3. And so that's your inverse function. Then you just rewrite it in function notation. So you write f inverse equals x minus 2 over 3. And that's your inverse function. Now, is the inverse a function? Yes, it is. So we're going to graph this in a moment, but it's just another linear equation, right? You can write this as 1 over 3x minus 2 over 3. Okay, so we're going to graph both the function and the inverse. So let's look at 3x plus 2. So this is a line, the function is 3x plus 2. So this is a line with a y-intercept of 2 and a slope of 3. So rise over run is equal to 3. And if I can do this right, I think that should work. Okay, so there's my line, y equals 3x plus 2, so f of x equals 3x plus 2. And then we have the inverse, which has a y-intercept of negative 2 over 3. So we are, well, let me draw the reflection line. So y equals x. I can do that. That'll help us visualize and see everything. Okay, so there's my line, y equals x. And now in green, I'll draw the reflected line. So rise over run is 1 up, 3 over. Okay, so it is still an increasing function. The slope is just different, and I have a y-intercept of negative 2 over 3. So it's pretty hard to look for negative 2 over 3. But I have a point here that's going to be in common with the inverse, because that's a point that's along the reflection line. So your inverse function will share those common points. And from that point, I can draw my graph, because the rise over run is just using my slope. Rise of 1, run of 3. Rise of 1, run of 3. Rise of 1, run of 3. So then you just use those, find your other points, and then connect them with a curve. I mean, with a line, sorry. Okay, so there's my line. Whoop, there we go. And that negative 2 over 3 y-intercept is over here. Okay, it's pretty hard to pinpoint that, but by using the other points, such as this point that's along y equals x, that point is shared amongst both functions because it lies on the line y equals x. A reflected point along the line is still the same point on both graphs. And then from that point, you can use your rise over run to determine other points and then help you sketch the rest of that line. And you can see that the green line is a reflection on the original function. And this green line is my inverse function. You can label it too. Okay. All right, let's look at an application problem. Now, for a real-life context, such as a word problem, to determine the inverse relationship, we're not going to switch the variables. Instead, we're going to solve for the dependent variable. This is due to the cause and effect relationship between the two variables. So when examining speed and stopping distance, the relationship between the two does not change. So you can't just switch variables, okay? So in a question like this, the equation is used to convert from degrees Celsius to degrees Fahrenheit. This is the equation that's used, okay? Go on Google, that's the equation that they use whenever you want to convert from Celsius to Fahrenheit. Now the inverse of this function would be to find the function that converts Fahrenheit to Celsius. That's the inverse, okay? But we're not going to do that by switching variables. We're going to do that just by switching or by solving or isolating for the Celsius, degrees Celsius. So Fahrenheit equals 9 over 5 C plus 32. Isolate for C. So if I subtract 32 from both sides, F minus 32 equals 9 over 5C. And if I multiply both sides by 5 over 9, I'm going to get 5 over 9 F minus 32 equals C. So my Celsius, if I want to convert from Fahrenheit to Celsius, this is the formula that I will use. Okay, and so I can write this as C as a function of F equals 5 over 9 F minus 32. Okay. And that's how you do that. Back to functions. Now let's look at a quadratic. What would that look like? Determine the inverse. So this one is just a function. It's not a word problem. So you can write it as y equals x squared plus 5. And to determine the inverse, you're going to switch the variables. X becomes on the left side. X squared becomes y squared plus 5. And now we're solving for y. We're going to isolate for y. Okay? So if I do that, I'm going to subtract 5 from both sides. X minus 5 equals y squared. And to isolate y, I have to take the square root of both sides. So the square root of x minus 5 equals y. Now remember, when you take the square root of something, think of like square root of 36, your calculator will tell you 6, but there are two answers. The other one is negative 6, right? Because negative 6 times negative 6 is also 36. So when you do the square root of something, you have to have two possibilities, plus or minus, just like the quadratic formula. So I'm going to actually have something that is not a function. Okay, so we're going to graph the function and its inverse. So x squared plus 5 is pretty simple. It's a parabola here at y-intercept of 5, and it will go up like this. Okay, however, the inverse is a little bit different. So what if, to graph this inverse, I might need to do a little table of values. Okay, so x and y equals the square root of x minus 5. So if x is, let's use x equals positive 5. What's the square root of x minus 5? Well, that's going to be 0. Square root of 0 is 0. Okay. Well, I can't use 4 because if I put 4, I'll get a negative square root, and that doesn't work. I can't use 3, it doesn't work. So I have to go higher than 5. So 6. So 6 minus 5 is 1. Square root of 1 is 1, or negative 1. 7, okay, 7 minus 5 is 2, square root of 2. Well, you can have plus or minus the square root of 2. Look at another number that we can do. Let's do 9. So 9 minus 5 is 4, square root of 4 is 2, so 2 or negative 2. And let's see, what about 14, right? So 14 minus 5 is 9, square root of 9 is either 3 or negative 3. So if I plot these points, if I start from 5 and 0, okay, I can then plot 6 and 1, and then 9 and 2, okay, and then, well, I can't go to 14, so this is good enough. So just create a little curve right there like that, but you also have these negative values. So you have 6 and negative 1, 9 and negative 2 as well, and then the parabola, sideways parabola, can go this way. Okay, so as you can see, this is my inverse, but it cannot pass the vertical line test. Right? If I put a vertical line, it will not pass because it will hit 2 points. So not a function, but it's still considered the inverse, right? Because it's still a reflection on the line y equals x. So if I plot the line y equals x, okay, this parabola is still a reflection of that one, vice versa. Okay, so that's my f of x. Here's my inverse. It's just the inverse is not a function. So is inverse a function? No. Why? It does not pass vertical line test. So think of vertical line test. Use a straight ruler, vertical ruler. Does it hit 2 points? It does. One there, one there. Not a function. So what would you do to make it a function? Well, if I did not have this bottom portion, it would now be a function. Okay, so what restriction would you make? Well, I would have to restrict the domain of f of x, right? So what would that look like? Well, let's talk about the domain of f of x. The domain, what's the domain of f of x? Every real number. What's the range? Well, y is greater than or equal to 5. So on the inverse function, the domain becomes the range. Y is the limit of all real numbers, and the range becomes a domain. x is greater than or equal to 5. Okay, but I don't want y to be all real numbers. I need y to be positive. Okay, I need y to be greater than or equal to 0. So what do I do to the domain? I have to make the domain greater than or equal to 0. So that means I have to also erase this part of my parabola. I can't have any x values that are negative. And so there you go. Okay, so that's our look at inverse functions, and that ends this video.